selection aspect. Okay. Please stop me if you have any question. I'm happy to have more interactions here. All right. So in recent years, there's a kind of paradigm shift in machine learning, or maybe in general data science as well. So in the classical machine learning, or we can call it supervised learning, we have labeled data, or here annotated data. So let's say we have some data of some documents. We want to classify it as, say, with positive sentiment or negative sentiment. Then we label them, and we can train a neural network with the input being this document and output being, say, plus or minus. Okay, and then we hope this trained neural network can predict well on the unseen documents as well. So that's what we do in the past several decades for supervised learning or statistics or data science. That's what we're doing. But in recent years, there's a big paradigm shift in machine learning, where instead of collecting a lot of labeled data or annotated data and train a neural network on them, we first collect a lot of, hopefully you can see my mouse here, like unlabeled data or unannotated data, and we use it for pre-training. Okay, and this data can be very kind of noisy or low quality. That's fine. You just gather them from internet. There's no label for it. Okay, but you can still try to learn neural network to learn the representation of the say document or the sentences in the document. So here by representation, I just mean a vector that kind of summarize the most useful information of the sentence or document. That's what we mean by representation. I'll talk about how do we actually learn it in the next slide, next couple of slides. But basically the main idea is just you use unlabeled, maybe low quality data, and then you train a neural network so that you can learn a function that maps a document to a vector, and we call this vector representation. Okay, so this step we call it pre-training, because we are not using this neural network for our, say, target task or a classification or anything. We just want to learn a good vector representation of the input document. Okay, so after we train this neural network on the top, and then we have, now we turn to our target. Say, let's say our goal is still to classify whether this document is a positive sentiment or a negative sentiment. So we still need, so there are two ways to do it. One is called fine tuning and one is called zero-shot prediction. For fine tuning, we still collect a little bit of annotated data, and we use those data to further train this neural network with the initialization being the pre-trained neural network learned from this unlabeled data. So that's called fine-tuning. So basically, we use the original neural network as initialization and further fine-tune it. There's another way called zero-shot prediction. I'll talk about that later, but basically, you don't need any label for it. You can still learn, you can still do prediction, and the classification accuracy is quite high. So this is the current, especially in recent years, this is a kind of the dominating trend in machine learning. It's been widely adopted in various applications. So these are some new applications like content creation, like generating images, kind of using similar ideas, AI agents, Copilot helping you write code, summarization of the document, and of course, we know ChatGPT now is being used in many places. Okay, so this is a quick introduction of the foundation model, pre-training, and representation learning. And the main driving force for this advancement is this basically this pre-training data. Okay, so you can get this pre-training data very easily, very cheaply, because you can just crawl from the internet. Okay, and the images, video, or text, you can use all of them as your pre-training data. Okay, and these are cheap, so you should just use them as much as possible. Okay, so these are the trend in recent years up to 2022, and this trend is basically growing exponentially. But now we're using billions, or now if not trillions of data for training these big models. Okay, so this is the current trend, but there's always a problem, which is the cost of training these big models. Okay, so these are some statistics of GPT-3, which is not even the state-of-the-art model nowadays. Now we have GPT-4, or there's some rumor we will have GPT-5 in this year. GPT-3 appeared in 2022. It has 175 billion parameters. It used 45 terabytes data, trained on 10,000 GPUs. There's some estimation of the cost is like 10 million. Okay, so you need to use a lot of money basically to train it. Okay, and OpenAI can train it, but in most kind of smaller organization, you cannot really afford to train it. Okay, so how do we kind of reduce the cost so that even for smaller organization you can still use it, or even for big companies, the cost is always a problem. So we want to reduce the cost. So in this talk, I will tackle the problem, or kind of try to solve this problem, the cost problem, from the data perspective. We try to do data selection for this pre-training step, okay, to learn a good representation. Okay, so here are just two motivations. Generally speaking, the resource is always not enough. Okay, the resource can be the money, the GPU used, the engineers to clean up the data. And generally speaking, the resource needed scale with the number of pre-training data you use. So the larger data you use, you need more resource. Especially nowadays, GPU is super expensive, so you want to reduce the usage of your GPU, or use what you have as efficient as possible. Okay, so you want to select the most useful data, because now data is cheap, but you want to select the most useful ones to learn the good representation. Okay, so that's the first part of the talk. We'll try to adopt this problem in a specific setting. And in the second part of the talk, I will talk about one particular usage of this representation learning or foundation model paradigm, where in many cases, we don't have, we are not that ambitious like ChatGPT. We want to develop a generic model that can do many tasks, but we have one or a few target downstream tasks that we really want to solve. And in that case, we still want to use representation learning, this paradigm, and how do we effectively leverage this particular goal that we have only a few target downstream tasks and based on this particular task to select the most relevant data in pre-training step for this target downstream task. Okay. All right, so in the first part, so there are two parts. In the first part, I will talk about our data selection scheme for multimodal contrastive learning. I'll talk about some background, and actually there's a benchmark developed from UW, and our algorithm motivations experiment. And the second part, I'll talk about the active multitask representation learning. That is for the case that we have one or a few target downstream tasks, and how do we select the most relevant task. There's some key notions called diversity and task relevance. I'll describe those later. Okay, so let's start with the first part, multimodal contrastive learning. So here, let me give you one concrete example for multimodal contrastive learning, and it's a very influential paper called CLEAP. Okay. So this is called contrastive language image pre-training. That's why it's called CLEAP. So basically, the data is of the following form. So it's a pair data. Okay, so each data point you have a pair of image and text. So if it's high quality data, then this text precisely describe what this image is. But of course, you will see some example of the low quality data where the text and the image kind of completely irrelevant to each other. Okay, so basically we gather this kind of pairwise pair data, and then we use this to train our representation. So here, just remember, representation means a vector that summarizes information of either the image or the text. So here, for multimodal representation learning, we hope that the representation for image and text lie in the same space. Okay, so basically the representation vector for the text and the image, they have the same dimension, so that you can actually do some linear algebra or like inner product on top of this representation even from two modalities. All right, so the algorithm there is quite simple. Okay. So the goal here is to train a good representation function that maps the image or text to this vector. So we call this neural network or this representation function encoder. So we have a text encoder for text and image encoder for image. Okay. So we'll just assume that the output of the image and the text, they are normalized. So their norm is, let's say 2 norm is 1. Okay. And so here, notation-wise, this II means the image representation, this vector of the I's data. And the TJ represents the text representation of the J's data, okay, for the text. Okay. So to learn this neural network, what we're going to do is to define a loss, and then we just use SGD or other algorithm to do training. Okay, and in PyTorch, as long as you can define the loss, then the rest is pretty simple. Just use the optimizer to train it. So the key part is how do we define good loss that capture, basically can help us to learn this good representation. Okay, so in this CLIP paper, this is their loss design. Okay, so loss has 2 parts, one for the image, one for the text. Okay, all right, so the key notion here is called QIJ. It's also called CLIP score, or basically like a score. So it is just so QIJ is inner product between the image representation and the of the I's data and the text representation of the J's data. So intuitively, it means that if text and image, they are actually the text actually describes this image, then in the representation space, the representation should be close as well. So their inner product should be large. Right? That's the intuition. So their norm is bounded by 1. It is 1. So if this inner product is close to 1, it means that this image and carefully or precisely describe this this text precisely describe this image. Okay, and this is their loss design. Okay, so so you can see here for the loss of the image, so this is kind of a softmax representation of the QIJs. In the numerator, you have QII. Okay, so this represents that. So if this for a given image or even given image text pair, if this text actually describes this image, okay, so that's correspond to QII, the inner product between this part, I status image representation and I status text representation. This inner product should be large. So that's why it's in the numerator. And you also normalize it because in the denominator, you have this QIJs. This compare each data point, so each image with other data's text representation. That's QIJs. So you hope that you're maximizing this CLIP scores QII in this normalized fashion. Okay. So that's the intuition. And similarly for the loss for text, you have QJJ in the numerator and say QIJ as normalization in the denominator. Okay, so that's the loss design. Okay. All right. So and in practice, you just collect some data in one batch to compute this denominator, and then you compute this loss. You can do backpropagation SGD to train it. Okay, so that's how how we train this CLIP model. All right, so how do we actually use it? So let me give you an example. How do we, without any label data, you can actually use this trained CLIP model to do image classification. Okay, so here's what you do. So here you have a image of a dog. Okay, so now you generate, so here what we call a template. This template is a photo of object, where object is something you can input. So this is an image classification task. Let's say you have 1,000 classes like ImageNet. So and each class, it has a corresponding tags. Okay, like say plane is a class, car is class, dog is a class. You put this the name of the class into this placeholder. Okay, so now you have a sentence. Now you use the sentence input to your trained text encoder. okay, then now you get a representation. So now you can get a representation or this vector for all the classes, okay? And then you also have an image encoder, which gives you a representation for this image. So now you compare this inner product again for this image representation and the representation for the text, okay? And then you just choose the class that basically use the largest inner product. So that's how you do classification. Okay, so you don't need further label data for this image classification task. Intuitively, in the original image text data set, you already learned good enough like information about text and image and their correspondence. So just doing this, you can give you high classification accuracy. And this is indeed the case. So it's a benchmark image classification data set called ImageNet. So here, this is round 62. This is zero-shot classification using the scheme I just described, okay? And it's comparable to other schemes. And in particular, it can match the performance of fully supervised ResNet 50, which is using like 1 million label data trained on this ImageNet neural network data set. Okay, so even without any label data, particularly for image classification, you can get very high accuracy for this using this CLIP model. Okay, so this is a big improvement over the previous approach. Yeah.
Can you just briefly describe the few shot?
Yeah, so there are other types of representation learning, which first learn a good representation of the image just for the image. And then by few shot, it means every class, I give you 1 to 16 number of data. And you can still fine tune your classifier on top of some representation. So this plot is comparing this kind of zero shot without any label with those existing representation learning approach plus some few shot fine tuning. Yeah. So quite surprising that without any label, you can still get this big strong performance here. So afterwards, this CLIP model has been used in many places like image generation, robotics, and now kind of a standard approach, even using like ChatGPT and other like foundation or large language models for capture the image representation. Okay, yeah. So that's not label, right? So, or not exactly the label. So, so in our pre-training data, it's something like this. It's a text that describes the image, but it is not particular for this image classification task. By label, I mean, a label specific for the image classification. But yes, of course, this text has some information related to the label. Without it, it's kind of impossible. Some things captioned, some is from the internet, and people kind of do some filtering, and yeah, it's from a lot of places. It's not like a single source data. Yeah. So now let me describe the data actually. So what's the problem of training this CLIP? So actually this CLIP model with a strong performance use 4 billion text image pairs, and these are carefully selected image text pairs. Okay, and and those data is actually not open source. They are using OpenAI, but not open source. Okay, they spend quite a bit of money to actually create this data set. Okay, so those are very costly. And can we obtain similar high quality data? So data is very important for train this CLIP. Like you can imagine if the text and image are completely irrelevant, you cannot train good model. Okay, so data is very important. But can we obtain lots of high quality data in a cheaper way? Okay. So one choice is that you still just scroll from the internet, web curated data. So for example, in Google, you search for some keywords and get some image, and you just use a keyword and the image as one pair. Of course, it's very low quality, but you try to learn something from it. Okay, so first gather a lot of data, and then you do data filtering. Okay, so this comes to this DataCom paper developed in last year from UW and UT Austin. It's a large group efforts basically try to benchmark this process. Okay, so it has a common pool data set. It has a kind of low quality data set with 12.8 billion image text pairs. So these are some examples. So you can see here, on the top right, these are kind of high quality data, like corns and tomato salad. This is actually a corn tomato salad. But here you have some shape, but the text is kind of completely irrelevant. Okay, so, and those are in the real data set also. And here are some images that are kind of blurred. Okay, there are many other problems I'll describe later. But your goal to benchmark it is just to select a small amount of data and train a CLIP model, and you compare the performance. So that's why we can, set up a baseline, a benchmark, so people can develop methods to keep improving upon it. Okay, so the benchmark training process is like this. So you filter data from pool of low quality data pairs, and you train a CLIP model. But now we fix architecture and hyperparameter. So training part is actually fixed. Okay, all you need to do is to select the data. And here for fair comparison, say we fix the total number of training data seen, which means that, for example, if you take one pass, say SGD or 4 billion data, we say it can be compared to 4 passes of 1 billion data of SGD. Because in terms of GPU compute, these two are comparable. So here are some examples of the training data. They have different languages. Some are low quality, some are high quality. Yeah, so you can see here, for example, this one has no information about the image, right? Okay, so for evaluation, there are 38 zero-shot downstream tasks. What I described before is one example, and there are different tasks, including say CIFAR 10, CIFAR 100 are kind of standard benchmark in image classification, and ImageNet. Most are image classification tasks. Okay. So in the original paper, they provide some heuristic or kind of baseline method for beta filtering. For example, based on image filtering, they have but the main idea there in this baselines is that they use a existing CLIP model or existing say representation neural network. Okay. This can be from other sources like existing OpenAI's CLIP, or even from some low quality pre-trained neural network. So use the very few data to first train some neural network and use that to do some filtering. Okay. So, so one way to image filtering, use the image representation of this pre-trained model to some clustering and select groups that contain at least one embedding from say a target image, let's say ImageNet data set. Another one is more relevant to us. It's called CLIP score filtering. So this is what we defined as CLIP score as before. So remember, for one pair of image and text, you have representation for image and for text, and you compute their inner product. That is called the CLIP score for this pair. So one way to do filtering is just to filter out the data if this CLIP score is small. So it's kind of if you believe this pre-trained model is good enough, so CLIP score higher, it means that this data or this test actually describes this image. But you'll see there are actually some problems later. Okay, so here are some basic results. So if you do not use any filtering, so these are some scores for different data sets. So higher is better. So if no filtering, it's like 2.5 for ImageNet, average 3.2. But if you do some filtering, it can get significantly better to say 4.5, 4.8, or 16.1 of this for this data sets. Okay, so this is kind of the baseline and the background. So now let's come to what's the problem in this approach. Okay, so the one problem is that, so here let's plot, give you some examples of from low CLIP score to high CLIP score. So remember, CLIP score is inner product of the text and the image representation. Okay, so, all right. So if you look at, so let's consider those image text pair with high CLIP score on the right. Okay, on the top right is pretty good. I mean, the corn's tomato salad for this salad, which is pretty good. But if you look at down here, so those images also have very high CLIP score. For example, this one, and the tag is an inheritance of time is in itself a form of wealth. Okay. And this image actually has the same text as the text for this image. Okay, so of course it will have a high CLIP score because this representation actually already encodes the text in this image, and it's the same as the text from the text embedding. But actually, remember, what we want to learn is the representation of the image. For example, this image is a natural scene, so we want something that actually describes this natural scene instead of this a form of wells, right? So those image or those pairs are not useful for our purpose. We want to learn good representation, but these are not good data for the image for this purpose. Okay. All right. So kind of want to evaluate how informative of this data to learn good representation, but we need to kind of evaluate how the informativeness of the data. The motivation is to, for example, the size of data is large enough so that can cover, become selected data so that it's large enough to cover all the useful features in the representation. And we'll hopefully those learned features are useful for the downstream tasks like image classification. That's our task benchmarks. Okay, so here's what we propose. We call it variance alignment score, VAS for short. So here's a general description. So let's say we consider two modalities, basically image and text in our context, okay? And let's say F bar is our pre-trained model. It's map, say, image to an image representation and maps the text to a text representation, okay? So in our algorithm, our method, we'll use some other information as well. We call it sigma test. It's basically kind of a cross-covariance matrix of some test prior distribution. Okay, you can imagine it as a covariance matrix of the representation of the image space, or generally describing the image space. I will give you some concrete example later. All right, the VAS, the score for the I sample is defined in this way. Okay, so we have two parts. So you can, for the I sample, for say generally two modalities. So it depends on two things. It's the inner product of two, say matrices. One is sigma test, one is sigma I. Okay, so sigma test, as I described before, it is a expected covariance. So this is in defining expectation form, but we'll use some samples to approximate it. But it's an expectation over some, say, target distribution or task distribution. And this is it's a kind of outer product or the cross covariance of the say one modality and the other modality in the representation space. Okay, so it's an outer product or this cross covariance. So and sigma I is just a kind of rank one matrix. Okay, it is a for the ICE data's first modality M1, you compute this representation, and for the same data modality 2, you compute this representation, and then you compute this outer product. Okay, and then you compute the inner product of these two matrices. All right, so all right, so a little bit more detail. How do we choose this sigma test? Okay, so in our paper, we have two ways. One is to remember our downstream tasks. They are all images. Okay, so we want to have some a distribution or of what's cross or this covariance such that it matches the kind of underlying or the true image distribution. So we just use the image distribution, like image and 1K as to compute its covariance. So here in this case, actually we choose both M1 and M2 to be the vision or the image encoder. Okay, so to be the image. Or there's another way, instead of using any external data, we just use our own training data itself. Basically, we can do some like greedy reduction to remove the data and to approximate this sigma test. All right, and then another question is what modality we can choose. So remember, we talked about two modalities. One is text, one is image. Actually, there are three choices. We can choose both M1 and M2 to be the vision or visual only encoder. Okay, so actually in this case, this will be really a covariance of the representation. And if we choose M1, M2 to be one being visual, one being language or image or text, then this is a kind of a cross covariance for two different modalities. And of course, you can choose text and text modality as well. So in our experiments, we find that visual only performs the best. So I will show you some results later. All right, so here, let me give you some concrete example why we can select this the most useful or informative data. So again, this is the original plot I showed you from left to right. These are the increasing CLIP score. And from bottom to top, actually that characterized as different this VS scores. Okay, so as we talked before, so VS score, is inner product between two matrices, but if in the one sample case, you can also rewrite it basically is have this quadratic form. And if we use the modality to be being the image, then basically it has this kind of quadratic form. It's inner product or this quadratic form of a image representation, some covariance matrix from some prior knowledge, and the image representation again of this form. Okay, so you can see here on the top row, they have all high VS score. So this is intuitive, meaning that those images are useful for image learning a good image representation. So you can see here the ship, although the text does not correspond to the ship, but the ship image, it does, it's a real ship image. On the other hand, on the bottom, they have low VS score. Either they are quite blurred, or this kind of image is not, kind of realistic image, or this kind of image have a lot of text on it. It's not really useful for downstream image classification. Okay, so basically our goal is to select the top right. Okay, so CLIP score kind of measures how important or how the text and the image match, and the VS score measures how useful this particular image is for the representation learning or pre-training step. Okay, so here's a summary. So using CLIP score, you will select these two type of data. They are kind of high quality, but not very informative, especially for the bottom type 4. But if you just use VS, it's not enough as well, because there are some, this kind of image you cannot filter out. So the final solution is just actually combine these two. You can have high quality data and high, kind of usefulness of the image for representation learning. So here's kind of a concrete algorithm. We first use the CLIP score to filter out data. Then we try to do this data selection problem. So generally speaking, this is actually an NP-hard problem, but in practice, you just use some greedy removing algorithm and can just select the best one. All right, so here we have two choices. One is using some external data like ImageNet representation, or you can dynamically reducing or dynamic computing this sigma test by using the current training data. So we are doing a removal. So every time what are left, it can be used as these sigma test. Okay, so here are the results. The ones in orange, they are the original CLIP score-based filtering. And you can see here in blue, if we just apply this VS filtering technique, you can only obtain, it's pretty bad. I mean, even comparing with without filtering. But if you combine these two, you can boost performance from 0.8 in this column to 5.2. And for example, in the average over 38 data sets from 15.8 to 17.4. Okay, so basically shows that using a more advanced filtering technique, you do get better performance. Yeah. Oh, okay. So it's kind of normalized as well. Let's see. Okay, so here's a VS score. So remember this F image, they are normalized, so their norm is 1. And sigma prior is like a fixed covariance. So you can compare different score for different samples. only the relative magnitude matters because you're just deciding which one's larger, which one's smaller, so you can delete or add samples. So we have one Turing parameter, which is a number of data we select in the end. And so we set that as a hyperparameter, and we just remove data until we get to that number. Yeah.
So it's still not like task specific.
No. For this one, it's not task specific. Yeah.
So basically, alignment of two modalities that matches.
Yeah, exactly. Yeah. But okay, so the task data here, so we have 38 downstream tasks. So all of them are image classification. So we are not doing like for each task we use a different sigma test. We just use the ImageNet, which we believe is a generic useful distribution to capture the world of images. So yeah, it's not like each task we use a different sigma test. We use just one image sigma test for this step. Yeah, exactly. Yeah. Yeah, exactly. Yeah, that's a great point. So yes, you can, if you have some target distribution, you can replace our sigma test with some target distribution you have. So here for this benchmark, it is, kind of you just train once and you apply to all the data sets. But yes, if you have one target task, you can use this strategy. All right, so these are the results. Yeah, so basically the conclusion is using VS alone is bad, but combining VS and CLIP score together is better than CLIP score alone. So here's some summarization of the improvement, and this is kind of it's pretty significant on this benchmark. So we've also done some ablation studies. So say you don't use image as sigma test, use text or image and text, but generally we found that using image alone is best. But I think this is a data set dependent metric, because you may have other data sets that using text can be better. But for this particular data set, image or vision alone is the best one. And one side aside, there's some, if you are familiar with experiment design in statistics, then we are kind of doing the opposite of those experiment design ideas. So we are trying to maximize some basically a trace of some covariance matrix. Whereas in optimal design literature, usually you will trying to maximize the inverse, a trace of the inverse of covariance matrix. Let's say A optimal, V optimal, those kind of experimental design approach. So we try experimental design as well, but at least on this data set, experimental design approach doesn't perform well compared to what we are doing. So yeah, so maybe at least in this setting, the experimental design approach, which kind of try to maximize smallest eigenvalue, is not that helpful. Or there's many other there may be other technique to make experimental design more useful. That's kind of a future direction. All right, so in summary of the first part, basically propose this new method. You can use external prior information with internal prior information to serve as a task distribution. And this can be visually is useful, and together with CLIP score is very strong performance for this data set. And for future work, so this is a pretty new direction. This DataCom paper is appearing last year's NeurIPS, which happened in December, and our paper just posted on arXiv. I believe there are definitely more advanced algorithms to do data filtering in a more principled way. And here you can also leverage additional information. Here we just use some existing pre-trained model, but you can use something else. Okay. So I think I don't have much time, so I'll quickly go over the second part of the talk. So let's say here you do have one target task, and how do you select the relevant data? So here we are in this kind of fine-tuning stage where you first train a neural network to learn this representation. which we call the source task, or well, interchangeably use task and class in this part. And say target task, you only have a few data, say 1 to 8 examples per class, let's say 20 classes. So here's one simple example. If you use representation learning, you can get 50 to 80% accuracy, but without using it, you get 5%. So there was like some problem or a theoretical problem, like why does pre-training help, and whether we can use less pre-training data. So one crucial condition is called diversity. So it's related to like Tim's question, like say you want to classify your target task, you classify whether the image is cat or dog. But imagine your pre-training data is all about classifying which type of the cat it is. Then you cannot hope that the neural network can learn good representation for the second task or target task for classifying dog, because the neural network has no information on what the dog is. Yeah, so you do need kind of diversity so that the pre-trained data covers the information of dog, so that in the downstream task you can do classification well for this target task. Okay, so this is a folklore, and in our prior work, we give a formal definition together with some theorem to show that our definition is a sufficient condition. So in this work, we basically show that the key condition is that in the pre-training phase, the last layer of the neural network, say you have T different tasks, and dimension of the representation is K. Then you need the last linear layer of the neural network to be a full rank matrix. Okay, being basically means that the number of tasks needs to be larger than the representation, so you can cover the whole space of the representation. Right? If it's full rank, it basically can cover the whole space, and we can prove that this is a sufficient condition to improve the performance of the supervised learning without using representation learning under certain conditions. Okay, so this is our prior work. So what's more interesting or more ultimately interesting is how do we select the data. So say we have a target task. Okay, so the goal is the following. So for multi-task pre-training, want to select the most relevant pre-training task. So select most relevant classes in the image classification pre-training task for some target classification task. So the key notion here I trying to emphasize is this relevance score between like a pair of tasks. Okay, so want to capture how relevant one task related to our target tasks. And based on that, we can do sampling. Maybe you can sample more data from the more relevant task to learn this representation. So this is the formal definition. Okay, so let's say in the pre-training phase, in the last linear layer, you have this W star matrix, is a K by T matrix. And for the target task, your corresponding linear head or this linear vector is called WT plus 1 star. It's a K-dimensional vector. So we assume that is within the span of this K by T matrix. And then if it's in the span of this K by T matrix, then you can always interpolate this WT1 star using the columns in this W star matrix because it's in the span. However, there are many of these choices, right? There are infinite solutions for example, this equation. So we choose the one that has a minimum norm. So now this solution V is unique. Okay, so this V is a T-dimensional vector. Each entry represents the score of the say the ith entry represents the score of the task I and the target task. Okay, and this score is computed from this quadratic programming problem. So and then given this score, we can sample each task data. Instead of using uniform sampling, we sample according to the score. And we can show that theoretically using this important sampling probably improves the uniform sampling. So that's why it shows the doing some more selective data selecting data more carefully can get improvement in terms of sample complexity. And of course, this W star and WT star is trained during, is an unknown parameter for optimized unknown parameter. So actually in our algorithm, you need to iteratively train this WT plus 1 star, W star, and estimate the score, and then you can get the improved sampling and or kind of approximate optimal sampling for this scheme. All right, so yeah, so that's a high level idea. I think the main takeaway is we can actually define a relevance score using this quadratic programming solution, and this gives you a characterization of how relevant each source task is to the target task. So here's our experiment. Again, it's on some image data set. So here we consider 16 types of, so these are classification of digits, okay, from 0 to 9. And so you have 10 digits, and we consider 16 types of corruptions. So these are different types of corruption of the ordinary image. So now you can create, so you consider binary classification for each digit. So you have 160 binary tasks, and each target task, so each task is a target task, and each target we associated with 150 source tasks, which correspond to 10 digits and 15 other types of options. So this is our experimental results. Compare with uniform sampling, you can get huge improvement from, say, baseline error 8%, and you can improve to, say, 6.9%. So that relatively is kind of a huge improvement there. And generally gets improvement. You can see here on the right, this blue curve represents the uniform sampling error rate, and you can see here shift to the left, which shows smaller error rate. Okay, and on the left is a kind of improvement of each of the tasks. The lighter, the larger the improvement. All right, so in summary, so basically I want to convey the message that this active learning idea is very useful for representation learning. So in second part of the talk, I gave a formal definition to characterize the relevance of each pair of the tasks. And we show in theory and in practice, this is stronger than some passive sampling, just uniform sampling from each task. And for future work, so there are actually a big literature in active learning. So there are other techniques we can leverage here for pre-training data selection and representation learning. And nowadays, we do not completely train from scratch. Sometimes we do fine-tuning, and we can also consider doing fine-tuning using active learning for this fine-tuning. And here we just give one definition of task relevance, and there can be other definitions as well. Yeah, so lastly, let me acknowledge my collaborators, Yiping Wang and Yifang Chen. They are my students. Wenda Yan is a master student here, and Kevin James is my colleague. And thank you all. I can take more questions. Yeah.
So you train your network with just on the original data set. That's how you get your first iteration of W star.
Oh yeah, you mean the algorithm, right? So yeah, so the algorithm is kind of complicated. Sorry, I mean, it's not that complicated. So basically, the idea is, so you first train your neural network. So okay, so the actual algorithm operates in epochs. So you first use, say, 1/16 data to compute the first version of your W star and the WT plus 1 star. You come to the score, and then you use this score to do sampling using, say, 1/8 of the data, and then you update the score iteratively. Yeah, so it's kind of doubling epoch approach. So, sorry, you mean V star? Okay, so V star is defined in this way. Okay, so you have W star, which is last linear layer of the pre-training steps neural network. And WT plus 1 star is the last layer of the target task. Okay. And then because we assume that this WT1 star is in the span of W star, so there are you can interpolate, or there exists some V such that W star times V equals WT1 star. However, there can be infinite many solutions, right, for this equation. So V star is defined as those solutions with a minimum norm. Yeah, that's a definition.
So this is a very clever idea. Like, so is it computationally hard? Because for any future new task, like you want to predict this image, you need to get a
Okay.
specific weight for that image.
Okay, so let me clarify. So this is for a task. So each task can have many images. So it's you know, say you have 1 million tasks to predict, then you only need to do once for this step.
I see. So it first group the image into different tasks.
Yeah. You can say that way. Yeah.
So out of curiosity, so have you worked on like pathology slides or just like, you know, medical images before? Because I'm just curious as someone who works on images, and I never worked on images before. Like, do you imagine these type of tasks will still work pretty well if I handed you a bunch of like pathology slides, like things, images from under the microscope, when you know it's no longer about cats or dogs or planes? Like, would you have a belief that conceptually that'll still work pretty well, or is there something fundamentally different about like pathology slides under the microscope?
So I don't work on that. What I know is that people are trying, especially the first part of the CLIP model. So if you have a high quality text image pair for pathology, then it's still very useful. That's what I heard.
Maybe other questions. So maybe like bigger picture wise for my own education, what do you think are like areas of representation learning that most excite you, or like most exciting?
So in recent year, or maybe just 1 or 2 years, the most exciting area might be this multimodal representation learning. So now here I describe like text and image, but nowadays people use say videos, sound and 3D modeling stuff, and response to text as well. So you can use multiple modalities to train a good representation. Yeah, so those are the kind of the trend in this year and last year. Yeah, so that's a what's it called? Imbalance problem. So it depends on your how to evaluate in the downstream task. If your downstream tasks they're balanced, then yes, yeah, like your training data is imbalance and the downstream task is balanced, then there will be a problem. There are ways to tackle it. Simplest way just to do some reweighting. But that's usually can have some effect. But I think more recent one is you try to create some synthetic data for dogs. That's usually the most useful way to boost performance. Yeah.
So some of the examples you showed us, you have 2 different modalities like text.
Yeah.
One could imagine an example where you have more than 2 modalities. If you have text, image, sound, or like image dimensions, for 3D processing. So in that case, would all of these methods extend to sort of a higher dimensional like tensor algebra or something?
I think that's one way, but I think the most standard way just do pairwise comparison. Yeah. So that's something that people have make it work, but yeah, maybe in the future you can use this tensor or other more advanced techniques.
Thanks, Simon. Yeah,
Right, thank you, everyone.